All right, today we're tackling a big one in physics, acceleration. And look, if you just think that means speeding up, you're about to have your mind blown a little bit. It's a concept that's way more powerful and honestly way more interesting than you might think.
Okay, so to get our heads around this, let's start with a little puzzle. Imagine a race, right? It's my car versus a Ferrari. Now, to make it a fair fight, we both agree to cap our top speed at 80 miles per hour. So who wins? You'd think it's a toss-up, wouldn't you? But it's not even close.
So here's the deal. The secret weapon isn't the top speed. That's exactly the same for both of us. No, the real difference, the reason the Ferrari leaves me in the dust, is this. It gets to 80 miles per hour in just 2 seconds. My poor car, it takes a full 10 seconds. That is the whole game right there. And this whole idea, how quickly you get up to speed, that's what we're really digging into today. It's not just about being fast, it's about the speed of speeding up.
Now, in the world of physics, this has a name, of course, acceleration. The official definition is the rate of change in velocity. But what does that really mean? Just think of it as a way to measure how quickly your velocity is changing from one moment to the next.
And, like a lot of things in physics, there's a handy little formula for it. It looks like this. A, for acceleration, equals your final velocity minus your starting velocity, and you just divide all of that by the time it took to make that change. Super simple, right?
So let's plug in the numbers from our race. The Ferrari's acceleration comes out to 40 miles per hour per second. My car, it's a measly 8. I mean, you can just see the massive difference right there. Every single second that passes, the Ferrari is adding another 40 miles per hour to its speed. I'm only adding 8. Yeah, that's why it wasn't even a contest.
Okay, now we're getting into the part that trips a lot of people up, the units. Let's take a second to decode what they actually mean, because it's not what you might think.
So the standard unit you'll always see for acceleration is meters per second squared. And I know what you're thinking. That sounds completely bizarre. What in the world is a squared second? It feels like it makes no sense. Or does it?
So yeah, what does that strange phrase, meters per second squared, actually mean in the real world? I promise you, it's way simpler than it sounds. And once it clicks, everything else about acceleration just falls into place.
Okay, here's the secret. Just stop thinking seconds squared. Erase that from your brain. Instead, think of it as per second per second. So, an acceleration of, say, 10 meters per second squared, it just means your velocity is increasing by 10 meters per second every single second. See? It's just a change happening over time.
All right, so we've got the speeding up part down, but acceleration is a bigger concept than that. There are some hidden rules here. It also covers slowing down, and it has some stuff to say about direction that might actually surprise you.
You know, a really great way to visualize all of this is with something called an oil drop diagram. Just imagine your car is old and leaky, and it's dripping 1 drop of oil on the road, exactly every second. What would that pattern of drops look like?
Well, if you're speeding up, right, the distance between those oil drops is going to get bigger and bigger and bigger with each second that passes. That pattern on the ground shows you, plain as day, that your velocity is increasing. That's positive acceleration.
But what if you hit the brakes? Now the drops are getting closer and closer together. The car is covering less ground each second. It's slowing down. Now you and I might call that deceleration. But in physics, it's just negative acceleration. Why? Because the velocity is still changing. So it is still accelerating.
And what about this pattern? The drops are perfectly evenly spaced. Now this car could be flying down the highway at 100 miles per hour, but because its velocity isn't changing one bit, its acceleration is 0. Absolutely 0. It's a huge point. An object can be moving super fast but have 0 acceleration.
So this really sums up the whole direction thing. If you're speeding up, your velocity and acceleration are basically on the same team, pointing in the same direction. But when you slow down, your acceleration is actually fighting you. It's pointing the opposite direction of your movement. It's like a force pulling you back to a stop.
Okay, let's get to our final and maybe the most important piece of the puzzle. It is so easy to mix up velocity and acceleration, but they are fundamentally different things. So let's put your new knowledge to the test.
All right, here's a classic physics brain teaser for you. Picture an object moving in a perfect circle. Its speed is totally constant. The speedometer needle isn't moving at all. So, is it accelerating? Yes or no?
And the answer is a huge yes. It is absolutely accelerating. And here's why. Remember, velocity isn't just speed.
It's speed plus direction. So even though the car's speed isn't changing, its direction is constantly changing as it goes around that circle. And any change in velocity, whether it's speed or direction, counts as acceleration. Mind-blowing, right?
So let's just wrap up the big ideas here. The number one thing to remember is that acceleration is any change in velocity, and that means speeding up, slowing down, or just changing direction. And that weird unit meters per second squared isn't scary at all. It's really just a shorthand for saying meters per second every second.
And that brings us to our final thought for today. Now that you know acceleration is all about change in motion, I want you to think about your daily commute. From the second you pull out of your driveway to the moment you park your car, where do you see acceleration happening? And I think you'll start to notice the answer is pretty much everywhere.